So we can now make an alkyne. We can now turn it back into an alkene or an alkane. What else can we do with it? And a lot of the reactions with alkynes are going to follow um, basically what you already know about alkenes, right? So alkenes have this wonderful reaction where they react with HCl or HBr and they produce the chloride, right? And so if you take this and you were to add HCl or HBr, whatever, all right, so this triple bond is still going to react here and it's still going to kick off that chloride and you're still going to end up with some kind of um, R group. Oops. And that is going to then lead to a carbocation here, right? Because you've taken, in fact, I can color code this a little bit. It's the H, and then that's there, and then that was a very haphazard carbocation. You draw that right there. This is not the most stable carbocation, so that chloride is going to come in right quick and fill that in. And then you're going to end up with your final product. It's going to give you a mixture, really. It's where you have now a chloride right there. And if this were, say, an internal alkyne, which I started off with, I guess I decided against at some point. An R and an R. I've drawn a cis. You could very well end up with trans. It's going to give you a mixture. What it actually will do is if you have on the if you're really good, you can add one equivalent exactly of HCl, this is what you would get. Of course, that double bond being there with a halogen, it can go on and it can actually react with a second equivalent of so that can do that again, and then you end up with what it turns out to be. It likes to add to the same carbon, so you end up with the geminal carbon, right? And I wonder, why does it add to the geminal carbon? That's pretty strange. Well, you got to think, right, that you end up with an R, and you have, oops, R coming out here, H coming out here, chloride, and then that's plus. Now, your first inclination might be, though, that's electron withdrawing. Why would it stabilize a carbocation? But you have to remember chloride has a bunch of lone pairs on here that can actually stabilize that through resonance, which means that carbocation is going to be on the same part as there, and so that can attack, and then that's going to give you your geminal product, all right? Um, Unlike the hydrogen halide addition, which I've just illustrated here, straight halogen addition does not stop. The second addition is actually as energetically favorable as the first, which means that if you were to take an R double bond and feed it, let's lower that down because I've got a little bit there in the way, and you are going to feed it some BR, right? It's going to keep adding, right? It's going to go and it's going to add like nuts. It's going to give you a bromine and a bromine here. That's going to be the first one. Then it's going to be like, never mind, I want to keep going. And so you will end up with this tetrabrominated product because the halogenation process can't stop. It's just too reactive. Whereas the hydrogen halide addition, right? So that's just hydrogen halide. That's the hydrogen halide addition. And then this is just the halogen addition. Two different processes with slightly different outcomes, right? So while it is technically possible to end on the hydrogen halide addition, it's really neither of these reactions are extraordinarily favorable. They give a lot of crap, but they're doable. Now, another thing that you could do with alkynes, of course, is you'll remember your friend oxomercuration. Um, Now, it's hard to do a hydration of an alkyne as it turns out, without a bit of help. So if you want to add a bit of H2O across this, right? So remember in the alkene case, at least, if I will draw this and just right quick remind you that you had an alkene, and then you threw in some H3O, and it could do all kinds of amazing things, and then you would end up with an alcohol, right? Well, that doesn't work exactly the same way on an alkyne. You have to, in fact, it doesn't work that way at all on an alkyne. First of all, the double bond is just not that basic. It's not as basic as the triple bond is just not as basic as the double bond. So in order for this to really work, you have to have a catalyst, and you can use mercury. So you have a Mercury Oxymercuration process here too. And if you add that in the presence of water, so your mercury catalyst, double bond, triple bond, it's a sucker for mercury, and so that's going to give you a double bond product with a mercury coming off of it, all right? And then your carbocation, and now water can come and attack there, all right? So now that you have addition of water, all right, you see this very familiar product. All right, Hg, and then OH. Great, everybody says. All right, and actually the mercury's pretty keen to come right off. It's not particularly hesitant. You just throw in some acid, and you end up with this alcohol. Now the problem with this, it's not a problem, it's a feature, is that this compound is not stable. This enol, alkene, alcohol, enol, right? And in fact, I'll write that down here. This, let's just call it enol, is not stable. It wants to convert to a ketone. And so there's an equilibrium process here. I'm going to scoot all this over again. There's an equilibrium, and I've drawn it asymmetric, but really the equilibrium favors the ketone product. That looks like this. All right, and you'll note this is definitely an equilibrium because this hydrogen has moved over here. Okay, and this is what we'd call the keto form. And we call this whole equilibrium here the keto-enol equilibrium. All right, and this is an important equilibrium that's going to make itself known to you multiple times over. So it's worth understanding and appreciating how this whole process plays out. So let's just discuss it. The keto-enol equilibrium is going to exist. Any ketone, all right, that is next to hydrogens is going to have some equilibria process with its enol form. Because that hydrogen, one of these hydrogens, any of them really, will be able to move back and forth between the alcohol of the enol and the carbon of the keto form. Now, this reaction is particularly, at neutral pHs, the equilibrium would be very slow, but at either acidic or basic conditions, the equilibrium picks up speed, right? Now, equilibrium, of course, is not kinetics. You always have a preference over one or the other, and that preference usually is the ketone. But the kinetics of it change very much. In other words, the activation energy goes down when you start adding an acid or a base. And essentially how that works is if you start off here, so actually I can just take this, I can copy, paste, all right? And you add an acid, all right? So this is now going to be in acid. what happens is this double bond can then deprotonate or protonate itself, and you end up with the addition of a H here. And these lone pairs collapse down here, right? So there's never any sort of alkyne. In fact, if I wanted to, I'd probably just show it do this, right? I'd show two consecutive arrows. The lone pair of this alcohol collapsing down to form your ketone, and then this double bond here going and grabbing that hydrogen. And so what we would have here is actually the ketone already, right? And then that would be a plus charge. So that would then, this hydrogen actually then goes off, and you end up with the ketone form. All right. So as I have drawn it up here, I've kind of indicated that hydrogen and hydrogen are the same, that somehow just sort of migrates over. That's not 100% true, but it's true enough. In the presence of an acid, you can get this keto-enol tautomerization going relatively quickly. Now, in the presence of the base, which is another way that you can do this, you start back down here. Whoa. It's fun. I could just keep doing that. You see, I've got myself a little hydrogen here, and if you have a base, then we'll just say it's an OH minus, and that is going to go for the most acidic proton, which is that one. And you pull that one off, it's going to go right there. Now, this will have a resonance structure, right? So now I have an O minus of an R. In fact, I've got to now shrink all this down so it all fits. All right, so this can form a resonance stabilizer. I can just go collapse down there to make the double bond and put the negative charge on that terminal carbon. That is a resonance structure, proper resonance structure. No bonds are, no atoms are moving around. That's how I know it's a resonance structure. R, and then there's an H, an H, and a plus. Oop, not a plus, not a plus. Definitely a minus right there, and that's probably it's less favorable to put it there, but that is the position from which it will go, and it'll take the water that was just created here and that can grab that proton again and again give you your ketone form. All right, so the ultimate product that you end up with, and I'm going to just, having stepped that through, now I'm going to just once again just draw the very simple reaction. And if I were to say you've got an alkene, and this is going to be a terminal alkene, and we're going to do it with mercury in the presence of water. That's mercury salt. Your final product is actually a Markovnikov looking double acetone, ketone, right? And where did that come from? Why does it do that? Is because, again, Markovnikov style, puts the positive on the substituted or the more substituted carbon, okay? So the oxomercuration process produces a Markovnikov product. Now, let's say you don't want a Markovnikov product. You wanted the you want an aldehyde. You don't want an acid. You don't want a ketone. You want an aldehyde. How do you go about that? Well, easy enough. You can grab some. Oops. You can do some old boron chemistry, right? Now the borane that you use cannot just be BH3. Okay, that'll go nuts. You have to have a special boron compound, and it's got to have a bit of crap all over it just to keep it from doing too much. So these are big alkyl groups, CH3, CH3, CH3. These are sec isoamyl groups. All right. Boo. Like that's a big boron. And yeah, so it's still a boron go though, and so it's still going to go right. It's going to make a borane. So you're still going to end up with R, and it's still going to want to put the hydride, right? So you're still going to end up with this, and now it's a double bond, and then there's your boron positive charge there, all right? And there's your hydrogen, and then you've got your, we'll call them, what will we call these? These are actually, so that's a sec isoamyl, just call it Cia. Cia from the chandelier right there. And that's a negative charge because boron doesn't want 4 bonds. It's like, go away, hydride. And the hydride's like, all right. So it goes right there. And you end up with, you're starting to see how this is going to be anti-Markovnikov, aren't you? You're going to end up with an R group, double bond here, H, BR. I don't like that BR. We're going to call it B. I'm going to call it SiA2, sec isoamyl. And that's your hydride, your brand new hydride. I'm going to color that in so we're all on the same page. That is that hydride, that hydride, that hydride. And now you got this friggin' boron stuck there. So you know how to remove this. Same trick as the last time. Pitch in a little peroxide and a little basic conditions. And bada bing, bada boom. You're going to form, initially, of course, your OH, right? And we're hopefully all now aware that this is not long for this world. It's going to have an equilibrium. It's going to drive it this way. And that's going to give you an anti-Markovnikov style addition of an oxygen to give you, in this particular case, the aldehyde, right? So the oxidation, the borane product gives you the aldehyde. Now there are a number of additional oxidation processes that you can do on alkynes. So you can still do permanganate oxidation, you can still do ozonolysis, and they give you different products, okay? So your reaction now with your oxidations, so we'll just say these are your oxidation reactions. Oxidation reaction. All right, and this is we're going to start off with our R triple bond here. So we're going to do an internal alkyne, and then I'm going to throw it into KMNO4. Sounds like a radio station, doesn't it? And under neutral conditions. All right, so this would be neutral. And, well, you know this reaction, right? So this is the same sort of thing. Potassium permanganate goes in, and it forms, first it reacts with 1 pi bond, and then that gives you, you know, the R. That gives you the alcohol, all right? But of course, there's another pi bond because there's 2 pi bonds right there, and that gives you another alcohol and another alcohol. And, you know, you're going to figure out these alcohols are kind of a pain, right? Because that's not stable either. Having 2 alcohols on 1 carbon as a great way to end up kicking one off as water, and you end up with the ketone products. Ah, come on, buddy. Oh, oh. All right. Geminal diol produces an alcohol. So you end up with your O and your H, and you can kind of see that you've got OH, right? Water. So one water is going to leave, that bond's going to break, and it's going to come off as water. This is called a geminal diol, and they're just not stable. And you'll learn more that you'll learn more about two alcohols on the same carbon. They actually can do some pretty neat chemistry if one of them is carbon, has a carbon attached, two carbons attached to the oxygen, and that'll be in the next chapter. So this process under neutral conditions gives you a diketone. Now, if you are under basic conditions, potassium permanganate can go a little bit further. All right, so instead you are under basic conditions, you have a diketone product, and you're in KMNO4, classic old, and that heats up. You can end up with vis breaking and getting two carboxylates left. So you can end up breaking that in half and end up with your carboxylates. Now, there is actually a faster route to this, and that is through ozonolysis. So if you just take ozone, if you have an internal alkene and you treat it with ozone in the presence of water, you will end up with two carboxylates. All right. Both ends of the alkyne become oxidized to the carboxylic acid. So this is quite similar to the alkene reaction. And that is the extent of the chemistry you need to know for alkynes.